I'll talk about change data capture into Iceberg, and so I retitled my talk to Chill Data Capture. So no one else appreciates it. That's okay. So a little bit about me. The most important thing about me is my puppy. She's a Chesapeake Bay Retriever, a little over 2 years old now, and yeah, living her best life. We live outside of Washington, D.C., sort of in the countryside, so she's got a few acres to run around in. So I got started working in data through nuclear physics. So I was working at one of the experiments at CERN, which I think more people here will appreciate than when I give talks in the US. So high energy particle collisions, massive data sets, analyzing those to find very rare signals. And I've worked as a machine learning engineer. I've worked as a data scientist. I've worked kind of as a product manager, product strategist kind of person. My title is head of data at Upsolver. I do a lot of different things, including Chill Data Summit. So Rachel Horder and I are sort of run we don't do the event logistics necessarily, but we sort of plan which cities and sort of what sort of content agenda to cover, how to help you and our other attendees stay on top of advancements in Apache Iceberg. So that's me in a nutshell. And this talk is going to be on change data capture. If you're not familiar with the concept, no worries. I really believe in bringing everyone along. So the first few slides are just going to go over what change data capture is. We'll talk about the requirements for change data capture. By the way, am I speaking too fast? It's good. OK, great. Requirements, constraints, and trade-offs for change data capture, and then specifically challenges with change data capture in Iceberg, and hopefully some solutions that you think are good. OK, so change data capture, or CDC. I apologize, the slides can be a little bit wordy. Basically, when you have an application deployed in production, there are databases that help that application function. These are OLTP databases, or operational databases, sometimes called transactional databases. This is your Postgres, MySQL, SQL Server, et cetera, MongoDB. And these store the updated state of the entities that the application needs to function. So if I'm an e-commerce platform, for example, I'll have databases for my users, my items inventory, my orders, et cetera. And the different microservices that help my application run in production communicate with me as a database, and other databases communicate with me, and I have to send messages out, and all the communications are happening via real-time message queues. The database has to update its records for all of these different entities whenever a change comes through. So, and it does that in ACID transactions, because it has to maintain internal consistency within the application and make sure that all the records are up to date. So, and that essentially is just it's sort of table stakes for an application performing, right? You don't want, let's say, going back to my e-commerce example, someone orders the last piece of a specific inventory, like a shirt or something. I want that to be immediately updated in my record so that you don't go and order the same shirt, and then I promise to fulfill it, but then I can't because I only have one of it. So the way that these databases work is that they keep a transactional log of all the changes to the records, which are inserts and deletes primarily, and then when you combine an insert and a delete, or if you have a record already and you're updating it, so you're combining insert and a delete, that's an update. So these three basic kinds of transactions it's going to keep in its log, and that helps to, if the database goes down, you can recuperate the state of the entities from that. Now, fortunately, we can also use this to recreate the entities, not within the database, but externally as well, which we can then use for analytics. So bad idea to run queries against your OLTP or operational databases for analytics, because it has to have its full attention on the application, but very good idea to replicate that data in an analytics environment and run queries there. So an example might be, well, how many items that were ordered last week on my application have I shipped for now, so that I can go and if I'm behind or something, I can catch up. Okay, so that's what CDC is in a nutshell. And so how does it work? So the reason it's called change data capture is because the change data, these updates, inserts, deletes, are captured from the transactional log. And different databases do implement CDC slightly differently, so I'm sort of giving the overarching overview here. So what you have to do is you have to go and enable change data capturing in your database, and then it provisions a separate space where it kind of captures the specific events for the entities that you want to track, so for the tables you want to track. Let's say I want change data capture on my orders. So it'll go and say, if there's a change event for orders in the transactional log, I want to log it in this change table in sort of this area. And then it waits for change data capture agent to read those events off of that change table, and then you have to sort of remove it and clean it afterwards. So the agent, the change data capture agent, helps by it not only reads the messages off of these change tables and send them out in message queues, but also sort of watermarks which events it's been able to sort of replicate, which events aren't there yet, so that ultimately you don't miss any change events. So because if you miss a change event, then you end up in situations where you have like duplicate records, for example, of the same order because you missed the delete. So to have that consistency of the continuous change events, the change data agent, such as Debezium, will sort of keep track of that. So that's sort of one side of it, the CDC agent and the database working together to send out the change events. And then on the other side is actually receiving them. So this is more on the side of the analytical platform. We have to be listening to to those message queues and receiving those events, and then which is essentially a streaming ingestion, right? So it's usually coming in a Kafka queue, and then we have to merge or incorporate those data into my warehouse or lakehouse. Merged has an asterisk because there are different strategies, which we'll talk about in a second, for how you want to incorporate the changes that have happened to be reflected in your tables. Okay, so just to summarize as a recap, we want to capture all the change events for the topics that we care about, for the entities we care about. We send them out from the OLTP, receive them in the OLAP, and then we have to figure out how to merge them correctly for our use cases. Now, and this is a image from company Stream on one of their blogs. It's a nice depiction of what's actually happening. The database is receiving these instructions to insert, delete, et cetera. It's keeping its transactional logs. The CDC process is happening, and then that's getting forwarded to this orders table, which is in my OLAP analytics platform. So the faster that we can actually apply the changes that have happened in the database in my analytics platform, the more up-to-date and consistent my analytics data is, the replicated data is. And the more efficient I can have my CDC process be, the easier it is for the analytics platform to enable queries from different query engines. So we'll dig into those two things more. But let's dwell a little bit on different merge strategies for change data capture. So one mode is where you're merging all the updates like sort of one-to-one, and so you have an exact replica. This is what the database would do if it did go down for a bit. It would go to its transactional log and recreate the state exactly as was, right? So, and that's what we're trying to do in the analytics platform. We're not following the logs so much. We're just merging all the changes immediately so that, item ID, blah, 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 has these details, and that reflects the reality in the application right now. Optionally, we can keep deleted events or deleted rows as well. And because this is now I'm talking about my OLAP, I'm not so constrained by space or compute and stuff. So I can, I have choices to keep data as well. This doesn't mean that I'm losing my data. It just means that the table literally should represent what the table is like in the database. Another use case is that I'm doing a change log replication where I am actually just getting the logs out. So for every record, I will, so the primary key, instead of being like the item ID, is more like the record timestamp or record ID of some sort. So I'm appending everything, so I have a full history of how a record has changed. There are also, so those are sort of the main two modes, but there are also more sort of intricate things that you might want to do, such as you want to replicate to multiple different analytics platforms. And we actually have a lot of customers that do want to do this. They want to replicate to Snowflake, they want to replicate to Iceberg, they want to replicate in other places as well. So there's, when you're doing CDC, you have to think about, okay, how do I read out of these change tables only once, because I don't want to overburden my operational database, and I also don't want to waste compute if I don't need to, and then write to multiple different sources. And that can be different targets, different modes. So in one place, I want to keep my change logs, and in another one, I want the exact replica. So I have all of these options available. Many tools don't support that for CDC, but these are like use case driven. As I said, like we see a lot of people wanting to do that. We can also consolidate on merge. So you can have your, you have a distributed architecture, you've got your application deployed in a lot of different places, and you're doing CDC on all of the instances. You might want to merge them and consolidate them together so that the table in your analytics environment is a full table of the entity that you're replicating. And then finally, you might want to do transformations on merge. So this is where instead of just taking the data and incorporating it into your OLAP, you are maybe joining different sources, doing some transformations, casting types into other types, and so on and so forth, doing data quality checks. Okay. Some people are falling asleep. No, I'm just kidding. But I got your attention. Database replication, as I said, is inherently a streaming process. So, okay, now we're talking about the requirements and constraints, et cetera. So it's a streaming process, and that means we have to be ready to receive the data when they arrive. So it's not a we can't like say, oh, get all the changes from yesterday. That's not really how that works. And that means scaling up and down when the production workload changes as well. We already talked about the different kinds of merge strategies, so we incorporate the changes exactly as we want them. We have to validate the data as they arrive as well. This means handling schema evolution. In a production database, things can change. Like as a data, I'm assuming most of us here are on the data side more. On the data side, we don't really, there can be a contract and an understanding and whatnot, but we can't really say, okay, you can only give me this table in this format, because the application engineers will do what they need to do to keep their applications running. So the schema of the tables and the change data can change. So being able to adjust to that, adapt to any schema evolution is an important part of doing CDC well. Similarly, setting quality expectations, like if I have a column that I don't expect to have certain values, then I should be able to sort of assert that as the CDC is happening. There are other things that we need to think about for CDC. For example, managing the size of the table. Just because we have, we're less constrained by storage in an analytics environment doesn't mean that we should waste storage and we should let the table sprawl or something, right? So what we need to do is we need to optimize the table layout. We need to make sure that there aren't like thousands of different small files to read. We should combine them when we can, and we should delete old stuff when they become irrelevant. And all of these things together, plus some effort on the query engine side, will make for more efficient queries. And this isn't it. Like there's more considerations, but these are sort of the top ones that we need to think about with CDC. Okay, CDC and Iceberg. Iceberg is actually pretty good for a CDC. So that's great because everyone's moving to the lake house. And so it's a really good thing that Iceberg is able to do CDC well. So it's an open table format for managing all the metadata and stuff. It inherently supports acidity. So that's great because, again, we're talking about asset transactions in the database. I lost my presentation view, by the way, but I have it here. So again, and then schema evolution, Iceberg is quite good at handling because typically when a schema evolution happens, it's only a metadata level operation as opposed to writing a bunch of rewriting a bunch of data files. It's you'll have these slides later on. There are many reasons why Iceberg is good for change data capture. It does dynamic partitioning, or it is able to do dynamic partitioning. Unlike the Hive days, we don't have to rewrite. I mean, this is being able to do schema evolution well. We don't have to rewrite all parts of the table that have already been written through CDC. We can say, this point onwards, this is the schema, and you can run a query on all the data that incorporates that schema evolution. But there are some challenges. Skip a slide. Okay. So one of these is that change data capture, because the transactional database is being updated constantly as the things in the application changes, there are lots of frequent updates. But on the other hand, in Iceberg, I think JB went over sort of the architecture of how changes are implemented. Every commit has to be a new snapshot to sort of keep track of where the table's state is. So that means that the writes have to be very efficient. When the engine that's doing the change data capture is writing the data in, it should be able to do it very quickly because new changes are constantly coming. This means we defer a lot of the merging of the data at read time. So when the query when the query engine is running a query is when it is going to be able to merge the updates and deletes, et cetera, into the data files. And not only that, but the merge on read has to be efficient as well for the same reasons. And one of the ways in which this manifests is in the efficiency of incorporating delete files. So specifically, Iceberg supports equality deletes, which are great. So the other alternative is positional deletes, where when an engine is writing the deletes, it has to scan the data files and then see where the rows are, where the data is stored for the different rows that need to be deleted, and then have a file that says, hey, go into this file and find this bit and then delete that or something like that. And that is computationally intensive at write time, which we don't want. So equality deletes are good because essentially what they do is they generate a filter predicate that you apply. So for example, you can say where order ID is this, and these other conditions are satisfied. And it can be as simple as like 1, right? Or it could be like a few different columns. These are the values. When you find that, then delete it. So that you can actually read the file and apply the deletes at read time. This is sort of the idea. I mean, there are, of course, always improvements to equality deletes as well, but equality deletes are strictly better than positional deletes, and Iceberg does implement them, but the rest of the ecosystem hasn't quite caught up yet. So many CDC writers don't actually support equality deletes. And although some query engines do, or many do, not all of them support equality deletes either. So there's definitely work to be done there as well. Another way to get some performance boost out is by merging equality delete file, or any delete file, by merging them together. So you get like small files that say this change, this update, this delete. What you want to be able to do is combine as much of that information as you can before sort of deferring the merging. Okay, so there's an example. Presto used to have, until a few months ago, used to have this sort of kind of inefficient merge on read implementation where, so these are like delete files and those are the data files. Okay, step back, the data files are representing the state of the table right now, and then these new delete files come in to say, delete these rows. What Presto would do is it would generate these splits where for every data file, the split would be generated around the data file, and it would include all of the delete files, and then go through and check, does this file have this row that I need to delete, and then so on and so forth, and do it for all the delete files. So it's a very an outer product issue where confounding errors. So this meant a massive I/O amplification at query time. A better approach is we do the table scan once, right? So we sort of scan the data files, and we scan the delete files, and or only once instead of scanning the delete files in every split. And then we do a filter based. There's more details of this in a blog I can share afterwards. But the essence of this is we do, because the delete files will always say when the delete came through, it has a sequence number. So every event, and this is especially relevant for change data capture, right, is stamped by this is a sequence number, and then the next one happens, and the next one happens. So you can read the delete files and say, okay, if, and the data files have the sequence numbers as well. So you can say, if this delete came in after this sequence number, it's just not relevant. So I don't have to apply it or look at that data file even to try to see if I need to apply it. You do that, and then that's sort of a broadcast join of deletes, and then you can get to the result that way. So it's like read once, right, instead of the previous scenario where we were reading as many times as there were data files. Another challenge with Iceberg and CDC, so chill data capture, is the managing of the update files that are being written. Again, the issue comes from the fact that there's so many updates coming through. So we need to, and then because the snapshots are being created whenever the updates are coming through, we need to have a method in place to not just have things blow up. So some strategy around compaction. That means rewriting the data and metadata files constantly. We're optimizing our snapshots. We're expiring old snapshots, managing that partition that's active, and sort of balancing that with the compactions that I'm running, that I'm able to run more on data that's not in the active partition right now. So there are lots of optimization things that you'd have to think about. I think I'll mostly skip over this, that Iceberg gives you the tools to do them, so it actually is pretty rich in, you can say this is what I want, this is the kind of compaction I want, this is the snapshot expiration, time frame I want, et cetera, but it's not automatically enforcing. So what you need is, you need some help, something to go and find the best strategy for doing those optimizations and then doing them, as opposed to sort of relying on users to be like, oh, I need to prune this manifest file, or I need to do something, optimize this table now. So in Spark and stuff, you can go and say Spark optimize Iceberg table, and then run it as a one-time thing. But it's more about a continuous compaction and optimization. Sorry, the talk is a little long. Concurrent writes, that's another thing that we have to pay attention to. So optimistic concurrency is a strategy that Iceberg uses for making writes, which, again, for frequent updates, you have a lot of things coming in real fast. And then if you're trying to do table management and optimizations in the background as well, then those things are competing with the writes that are coming in. So it's a balancing act of who gets to say, I have the table for now, I'm going to commit my changes, and then anyone else can take it. Optimistic concurrency just doesn't work. It's not like you lock and then you say you try to make changes. This is the details. You can look at it later. But basically, you try to update. You try to write the updates. And if something's changed in the meantime because someone else has managed to get in their updates first, then you have to sort of go back and start over from that new state. So you can end up in situations where you're retrying commits all the time, and things are kind of in tension. And occasionally, and it's very occasional, you might get into a situation where two things are trying to update the table, and they're both stalling. They're making each other stall. The solution to this, in my opinion, is to have the same engine that's writing the CDC also running the optimizations, planning and running the optimizations. Because then you're aware of the changes that are being written and when they're coming through, and when you have the right conditions to need an optimization and then be able to apply the optimization. Like you can prioritize which one's more important in a given time. I mean, rights should, of course, take precedence, but the thing is that you do need to have these maintenance tasks running. So the more aware they are of how the data is flowing in, the better it is. Last challenge with CDC and Iceberg is primary key enforcement. So it's basically a weakness, or more generally, like being able to validate the data. So running data quality checks, deciding what to do when you're not able to merge updates. This is a bit tricky. That's because primary key isn't like natively by default enforced in Iceberg, but it is required for CDC. Like you need a column to merge changes on. Otherwise, that's the whole concept of these entities that you're replicating, right? You have to have an ID that you're consolidating changes based on. So what happens is the user has to define, so go into the database and say, okay, this is my entity, this is a good candidate for the merge column, and then let the OLAP environment, in this case the Iceberg Lakehouse, know that this is it. But even then, Iceberg isn't going to go and enforce it, because that is kind of a foreign concept. So that validation that you need for your primary key column, is it not null? Is it sort of a value that I expect and is good? That has to be handled sort of externally. And that can result in merge failures, which are bad news bears for CDC. Okay, I'm done, I promise. Optimal CDC solution, ideal CDC solution, right, is where you can choose your CDC merge strategy based on the use case. You don't want to be forced to do an exact replication or merge only, append only CDC, because then you'll have to take, it's like stage, a lot of tools just let you do that merge only, or append only, sorry, and then you have the staging table, and then you have to do a bunch of transformations to actually get the replicated data, so it's like twice the storage, twice the effort, things like that. So, I'm sorry, this is not in sync with this by design, but that is making me say things that I don't want to say. Yeah, summary, we don't need the summary. This is where I was. So you want to be able to choose your CDC merge strategy based on your use case. But you also should be using merge on read with equality deletes, again, which is not enforced everywhere, or not even available in all query engines and all CDC writers. So there are some guardrails that you need in place while still getting flexibility to do what you need to do. You should be able to set your table retention policy. It's just data governance, data management, right? You don't want your tables to grow. But at the same time, you want automatic optimization so that you don't have to go in and try to figure out when to run compactions on a table, so on and so forth. So that's basically it. These are kind of high level, the ways to start thinking about how to solve the specific challenges that we talked about, which are here. And I will share my slides. And I'd love any feedback, or if you have solved it in a different way, I'd love to know that as well. Thank you. Any questions? I don't know if I can answer your questions, JB. It was with Yoni last.
Yeah,
it's over here.
Thank you.
Just wondering, one thing is, in a context of CDC, each time we have an event coming into an Iceberg table, it means that we create a new manifest list for each commit. And it means that we have to update the metadata.json. And I think that's the main performances issues.
Right.
So I wonder your thoughts about, instead of directly exposing the metadata.json to the engines, if we facade this metadata.json with something else do you think that it could help in the context of CDC, like optimizing the query engine? I mean, and also on the background of Iceberg, because it's super costly to recreate again and again the metadata.json. So do you think that it will help to facade this metadata.json with another layer?
So I want to dig into that. Who's the facade for? Is it for the query engine or for the? Okay, got it. Yeah, Yoni wants to answer.
Hi.
I can answer it, but Yoni is.
So this is actually something that we've been actively working on. So yeah, first of all, I mean, you do need to batch. You do need to combine the writes. You can't do a write for every input, obviously, because you're writing files, and it's not just one file. You have to write the data file, the metadata, the manifest list, and at least one manifest. So there's at least 4 files you need to write for every commit, and it just doesn't work at those scales. So you're definitely batching, and yes, like if you want to get to real time, you just can't do it through files. But you could have the catalog cache information and store it, and then kind of flush it when necessary, but then when a query comes in, it can spoof those files for the query. And that's something that we're actively working on in Upsolver to incorporate something like that to give you kind of up to the second latency. Today, with existing catalogs, you're going to generally get like on the order of, let's say, 1 commit per minute is let's say, the best you can do with Iceberg today kind of thing. Like I wouldn't recommend people go faster than that. Iceberg doesn't work that well at these low latencies.
Yeah, thanks. The question is, that's right, today we can cache the metadata.json through catalog. My question, and it's actually something that we think about features potentially for Polaris and other catalogs is, but he has to go into Iceberg, is I think that it's not so efficient to directly expose the metadata.json to the query engine as it is, raw. Because today is what the query engines are doing. They are just reading the metadata.json, and then they go on manifest files, manifest data files, whatever. My ideas, and I wanted to get your feedback on that, is if we abstract the metadata.json to something different that could be optimized for the query engines, I think that we can have a huge performance boost in the CDC context, especially.
Yeah, I mean, that's another way of saying, so the query engines are currently sort of figuring out, like, and so that's why you have the bifurcation. Different query engines are sort of coming up with different query plans based off of the same sort of metadata layout. So what you're saying is sort of not the query, but we'll lose, like, you know, the innovation that's coming from the different query engines trying to solve this differently.
But let's say on the metadata.json, we have all the commits for one table. I mean, maybe the query engine doesn't care about having all, but he has to parse and read everything, even if he has to consider only the last snapshot. Right. So through the catalog, if we say, okay, go to this REST endpoint, and you're going to get only the last snapshot for this table, then we're going to have a huge performance boost, I think.
Yeah, I definitely agree. I mean, the catalog is very well positioned to do optimizations because Iceberg as a format it's going to evolve slowly because everyone needs to kind of support any evolution. So for example, like JB mentioned, there's an issue today that the metadata file is one file and it includes all the history, all the branches, all the historic snapshots. But most queries only care about the current snapshot. So actually, I might be reading a file, and literally these files can get to be hundreds of megabytes in large tables. And especially streaming, because you get tons of commits. So you have this 100 megabyte file that you have as overhead to read every single time you want to query. Now, changing that in the spec is something that people are actively working on, and that would be a very good thing, and it would support things broadly. But until that happens, which might take years, catalogs can do whatever they want because they're a facade to the metadata file. So they can say, well, we'll support these weird things that aren't actually supported in the spec. Maybe we'll cache them. Maybe we'll put them in memory. And catalogs can then improve efficiency a lot. And we're talking about these are use cases that maybe don't matter to everyone. Analytics queries can often take minutes and hours. So then reading another 100 megabytes doesn't matter that much. But increasingly, we see use cases where people want queries to return in like 2 seconds. And then reading a 100 megabyte metadata file is going to be a bottleneck. So I think that these are very exciting changes, and as the amount of use cases supported by the lake evolves, we're going to see a lot more demand for these kinds of things. And I think that this is kind of the bleeding edge of where we can take a lake and how we can get more and more value out of the lake is very important.
Yeah, and maybe to bring it to a higher level for folks that are not as deep in Iceberg as these guys, right? There's sort of 3 layers. There's the Iceberg layer, right? Then there's a catalog layer, and then there's a query engine layer, and each of these can have a say in how to actually access the data, how it's actually going to do it. So, you know, it's always trade-offs and it's always a balancing act, especially with open source projects where, as Yoni said, things can take a while. So who should optimize that right now? Okay, yeah, one last question, and I think we have to move on.
Hello. So my question is general about CDC. So how do you do data reconciliation? How do you make sure that data is not missing?
Data is not missing in CDC? Yeah, so that's basically the change data capture agent, such as Debezium is sort of the open source most popular one, is going to, when it's reading off of the change table, all the changes, it's going to mark up to which number it's gotten. And it's been able to replicate out. And then the database sort of knows that, so it's not going to like get rid of it. So even if there's a downtime, you can come back and you can sort of get back where you left off, essentially. Does that make sense?
Yeah, thank you.
Sure. Shout it, please.
Thank you. So I think we have similar architecture of CDC replication through AWS DMS, so where we have a PostgreSQL database points to a S3 data lake, and then seamlessly replicate that into Snowflake. The current challenge we are facing is like DMS is not capable of replicating the DDL or like any alters on the source table. So every time you have to stop and restart the data pipeline, or like at times it's not seamless. There is a native property on AWS itself, which says handle all alters on the source table, but that doesn't work. Like how does that can you throw light, like how is it being handled from Iceberg or like Polre's point of view?
Yeah, actually, yeah, if Yoni is a database guy.
Hello. Yeah, so this is actually, so Iceberg itself supports schema evolution kind of conceptually, but like this is a challenge in DMS itself. So you need or rather in DMS, and then DMS is not writing all the way to Snowflake. You have like something in the middle, and that something in the middle needs to support the schema evolution as well as DMS. So Debezium supports that out of the box. So anytime there's a schema evolution, Debezium will know about it and just continue to seamlessly output records with the new schema. But then also the code in the middle, that's where Upsolver would come in, is that we would be that part that connects kind of between the database or between Debezium if you're using it yourself. And Snowflake, that code needs to know how to add columns, and it needs to go all the way to Snowflake. It needs to actually alter the Snowflake table, change the files that it's creating that are loading, and then upload those. So, and then there are also a lot of different rules. How can you do schema evolution? Because maybe like you had a column that was a integer and suddenly it became a string, and that's not supported natively in Snowflake. So what do? You have to like figure out what the rules are. So this is really a problem of the intermediate step, which, like you said, Debezium doesn't solve natively. Other solutions, Upsolver would solve it natively, but I mean that's basically where you're going to have to focus. It's not like conceptually in CDC itself, but that the pipe needs to just have those features.